So this is number 19, and it reads, one end of a uniform 4.0 meter long rod of weight F sub g is supported by a cable. The other end rests against the wall where it is held by friction as shown in figure P12.19. And the coefficient of static friction between the wall and the rod is mu static equals 0.5. Determine the minimum distance x from point A at which an additional object, also with the same weight Fg, can be hung without causing the rod to slip at point A. So I just read you the diagram right here on my paper, and I gave the length of the rod like a variable L, just to put everything in variable terms before we plug in the numbers. So they give you the length of the rod, which is 4.0 meters, and this coefficient of static friction between the wall and the rod, which would be at like this point right there. So that is 0.5, and then the weight of the rod is Fg, and then the weight of the mass that they want you to determine the distance where it could be hung without making the rod slip is also Fg. So first thing I want to do is draw a free body diagram, like labeling all the directions of the forces. So you have Fg at the center of mass of the rod, and then I just placed the other mass that they want you to find the distance from point A right here, just at an unknown distance. And then since it's hung, the rod is hung by a string against the wall, so there's going to be tension, and they give you the angle 37 degrees, so yeah, I just drew the angle right there, because like opposite interior angles or something. And then from against the wall and the rod, there's friction up, because that's the direction that the rod would slip. And then there's also a normal force pushing against the wall, so the resultant force would be straight down the middle. And there's an angle theta prime that we don't know. So next I summed up the forces. And you, in the x direction, you have the normal force of the wall, and then you have the x component of tension. So that's normal force of the wall minus t cosine theta. And since the rod is in equilibrium, it's going to equal 0. And you can solve for the normal force of the wall looking here and substituting r and theta prime in. So you'd get r cosine theta prime minus t cosine 37 degrees, which is the angle that they give you in the problem. And for the y direction, you have friction pointing up, friction pointing up, and then you have t, the y component of tension, so which would be t sine theta, and then you have Fg down and another Fg down. So you'd end up with F plus t sine theta minus Fg equals 0 again, because it's not accelerating. And friction is equal to the coefficient of friction times the normal force, and the normal force in this case would be the normal force due to the wall, or from the wall, sorry. So if you substitute that in for F, you get mu s, normal force of the wall, plus t sine theta minus 2Fg. And if you substitute what you found for the normal force in the x direction, you'd end up with mu s r cosine theta prime plus t sine theta minus 2Fg equals 0. And since we don't know what r is or what theta prime is, you can set the two equations equal to r, and things will start canceling out. So for the sum of the forces in the x direction, I set r equal, well, since it's equal to 0, you can easily like isolate r, and then same thing in the y direction too. So in the x direction, you end up with t cosine theta over cosine theta prime, and in the y direction, you end up with 2Fg minus t sine theta over mu static cosine theta prime. And then you set these equal to each other, and you should get this, and then the cosine thetas cancel out, right? So then you end up with the cosine theta primes cancel out. So you end up with t cosine theta over equal 1 over mu static times 2FG minus T sine theta. And then just like plug in the numbers in your calculator, except for like tension force due to gravity, because they don't give that to you. And you should end up with 2T equals 4FG, and then from there you'd find that T equals FG. And then this is the force that you're going to be plugging into the torque equation. So since this object is in equilibrium, the sum of the torques will equal 0. So for the first torque due to this object, the pivot point will be at point A, since that's that's the point where we have the most unknown forces. So the distance from point A to this is x, which is what we want to find. So I just labeled that x cross FG. And then the second torque will be due to like the center of mass of the rod. So that would be L over 2, because the length of the rod is L, and then the center of mass of the rod is at its midpoint. So L over 2 cross FG. And then the last torque would be due to the tension. So you do L, since tension is occurring at point B. So you do L cross T. And then like for vectors, when it's the two vectors and then multiplied by the sine of the angle between them. So the angle between them is what they give you in the problem, which is 37 degrees. So that's like what you would plug in right here. And then so you should end up with x times FG plus 2FG minus 4 times 2FG sine 37. And then this 2FG came from the tension that we solved for earlier. So you just plug that in here, and then L is from the length of the rod, and then L over 2 is also the midpoint of the rod, so you just do 4 over 2, and that reduces to 2. So when you plug in sine 37 and then multiply that by 4 and 2, you should end up with 4.81, and then everything's in terms of FG, so FG will cancel out eventually, and then you end up with, if you isolate x, you should end up with x FG equals 2.81 FG, and then FG's cancel out, and you're just left with 2.81. That's it.